Hi everyone, and welcome to this course on high voltage and electric vehicles. In this first module, we will explore the critical safety and the technical concepts that are essential for working with high voltage systems in electric vehicles. The idea is that at the end of this course you will have solid foundations in the principles of EV safety, and all of this will enable you to confidently apply this knowledge in the different engineering roles that you may have. So this is an overview of what we will cover in this module. As you can see, we will begin with a general introduction to electric vehicles, and we will review some of the trends that are currently shaping the future of mobility. Then we will move and we will have explanation or basic introduction to electrical concepts that will allow us to ensure that everyone in this course is in the same page regarding key fundamentals for understanding the EV systems, and particularly the high voltage systems. And finally, we will explore some EV voltage architectures and also some of the key components, high voltage components that are included in those architectures. Here we will focus also on the role, the design challenges, and some of the safety implications of those components and architectures. So let's begin. And to start, let's place maybe the electric vehicles within a broader context. Started with some of the trends that are currently shaping the mobility sector. So here I place four of the most relevant trends. First we have electromobility, then we have autonomous driving, shared mobility, and connectivity. So if I start with e-mobility, basically this represents the shift from the internal combustion engines to electric powertrains. And because of this shift, we introduce the high voltage systems, which demands a new approach for safety and reliability of the whole vehicle design and the whole vehicle operation. Then we have autonomous driving that is changing the role of the driver completely. So here we are moving towards vehicles that can navigate in the cities and make decisions completely independently. And this adds a lot of complexity to the vehicle system and also to the safety and operation considerations. Following, we have the shared mobility. This is changing how we own and how we use those vehicles. Instead of having only private ownership of a vehicle, here we have shared mobility that increase the usage rate and the operational demands of these shared vehicles, and it is also a very interesting trend. And finally, we have connectivity that brings the vehicles into a digital ecosystems. By having smart vehicles that are capable of communicating with other vehicles, with the infrastructure, and even with the power grid, we can dream on very advanced interconnected systems. This connectivity is crucial in some of the tasks of EVs, for instance, in optimizing the charging strategies and enhancing in general the vehicle efficiency. Following those trends, the rise of electromobility is evident, and as you can see here, it is exponential. There is an exponential growth both in the markets in Europe and in the market in the United States. This growth is driven by several factors that includes, for instance, stricter emissions regulations. The government is also creating subsidies for supporting electromobility, and also the consumer is having preferences for sustainable transportation and sustainable solutions. Alongside with those, the advancements in the battery technology and the charging infrastructure also plays a very important role for having this rise in the e-mobility in general. And this rapid growth also brings a lot of challenges, addressing the complexity, for instance, of these high voltage systems that varies across regions, for example. In Europe, there is a broader adoption of standardized charger systems, whereas in US, the market faces some challenges related to related to systems that are not standardized, and also with charging infrastructure that varies a lot from one state to another. Understanding all of the trends and all of these markets is very important for us to align the efforts and to meet the demands while prioritizing safety, efficiency, and sustainability in whatever is designed and supported. The shift of electromobility is not just about replacing the internal combustion engines with batteries and motors. It is a complete change in the vehicle architecture. Here you can see, for instance, that in a combustion vehicle, the drivetrain is dominated by mechanical components. Like we have, for instance, pistons, we have the fuel tank, we have injection systems, we have the differential, we have a lot of mechanical components. These components work all together to convert the fuel into the motion, and all of these thanks to complex mechanical process. On the other side, we have the electric vehicles, and many of these mechanical systems are completely eliminated and they are replaced by simpler systems, but more electrical complex systems. This transition also brings in the high voltage system that supplies the powertrain and also powers any auxiliary component, like for instance the cooling system, the electric heating, and the air conditioning. While these systems are highly efficient, they have new challenges related to the electrical safety, the insulation, and the electromagnetic interface, for instance, that will be the core of this course. Electric vehicles represent then the step forward in the technology, but as you know, they introduce new safety challenges. Here in this slide, we are having a closer look at some of these unique hazards that are going to be associated with EV. First, although is often overlooked, there is the risk of silent operation. Unlike internal combustion engines, the EVs produce minimal noise, and this increases the risk of accidents that involve pedestrians and cyclists. This has prompted regulation measurements, for instance, to have artificial sounds and generators for the EV to avoid this sort of accidents. Also, we have exposure to toxic gas. During a thermal runaway event, the lithium-ion battery can release highly flammable and toxic gases, such as, for instance, carbon monoxide. All of these gases poses a big risk and required advanced venting and also to contain the exposure to those gases in case of thermal runaway in the battery. Next we have the risk of explosion. In this case, if a single battery cell on our whole battery pack overheats, it can trigger a chain reaction and potentially even it can trigger a catastrophic explosion in that. This is often including some intense flames, and also in some cases there is debris that is ejected at high speeds that creates an additional hazard for emergency responder, for instance, or for technicians that are repairing those. Mitigating those requires robust safety mechanisms in the battery pack, such as, for instance, pressure relief vents and also fire-resistant materials that can contain all of these explosion and the flames that are generated there. Also, we have, of course, the electrocution risk that are inherent to the high voltage systems. EVs operate with voltage that can go up to 800 volts. Even right now, there are systems that has a voltage higher than 1000 volts. And this makes the insulation, the proper grounding, and the emergency disconnect of the system absolutely necessary and essential for avoiding the risk of electrocution in the system. Finally, we also have the risk of electrocution when the battery and the system is submerged. The interaction of water with the high voltage systems can create electrocution risks that are additional. All of these different risks emphasize the importance of a proactive approach to safety, a proactive approach to including safety measurements from the design to the production and then to the operation and maintenance of those vehicles. And we will continue then exploring and seeing how to dive deeper in that topic.